Alright gang, here we go. This is for Chem 1, Unit 12, Part 2. We're going to talk about acid-base theories, specifically focusing on Arrhenius. We're also going to talk about the difference between concentration and strength. Alright, so Arrhenius, the first thing that we need to establish is that humanity as a whole, we've known about acids and bases for thousands of years. Now, before Arrhenius, acids and bases were defined based off their properties, and not necessarily how they acted chemically. It was more like, well, this is sour, so it must be an acid. This is a bitter, it must be a base. Kind of like those general properties that we talked about in the last video. And then Arrhenius came along and he came up with the first theory. Well, what exactly is this substance doing in water? Okay, and so his definition was pretty basic. All right, and it's not very robust. He says it's an acid if it increases our H plus, or this hydronium, H3O plus, in solution. And we specifically, H plus and hydronium are interchangeable because really when we're making a hydronium, we're taking a water molecule and adding this extra hydrogen to it. So we get this hydronium ion right there. So you get the HCl with the H2O forming this hydronium ion. All right. So here's your reaction, HCl reacting with water, and it's increasing this concentration. It's making more of this, so therefore it must be an acid. And here's a little picture showing what's going on. This little hydrogen is attaching to this water, and you get this more of this hydronium ion here. And then bases increase the concentration of hydroxide, this OH minus. So here's your sodium hydroxide, and this guy's going to break apart into its two ions. You get the sodium, and then you get the hydroxide. And because there was more of this after it got put in, therefore it must be a base. So that was Arrhenius' definition of acids and bases. All right, so here we go. We're going to show how sulfuric acid is an Arrhenius acid in water. Well, if we got H2SO4, then we're going to react this with water. All right. Well, this guy would react, and so this would lose its hydrogen, and so you'd get the H3O plus, right? And then you'd end up with HSO4 minus. All right, and so that's that. Pretty easy, pretty easy. Okay, so we increase the concentration of this, so therefore it must be an Arrhenius acid. All right, down here we've got show how calcium hydroxide is an Arrhenius base in water. So we got calcium hydroxide. It's reacting with water. Actually, it doesn't even matter if it's in water or not because it's soluble, right? So we can just erase the water part of it because that's not really going to do anything to us because it's soluble. We know it's just going to break up into its constituent ions, okay? So that means we're going to get a Ca2 plus, and we're also going to get a hydroxide. Right, two of them because there's a two right there. And so because we've increased the concentration of the hydroxide, it must be a base. Pretty fun. Pretty fun. All right. Now, strong acids are acids that completely ionize in water. Okay, so these these guys completely go to their ion. So you got HBr is a strong acid. All of it is going to get turned into Br minus, and then the H plus that bonded to the water. All right, and this is because the polarity of the molecule is stronger. All right, the stronger the polarity of the molecule, the stronger the acid. And really, this bromine is going to be jacking the electrons from this hydrogen. All right, so we define these guys as strong electrolytes. These are your strong acids down here. You need to have these memorized. All right, there's 7 of them. 1, 2, 3, 4, 5, 6, 7. I'm going to teach you how to memorize them real quick. All right, so you're gonna start your paper here. You're going to be your strong acids, and you're going to number it to 7 because there's 7. 1, 2, 3, 4, 5, 6, 7. All right. All right, this is pretty cheesy, but you know, if it means getting the question right on the exam, it's worth it. So, number 1, hi. All right, so there's your first strong acid. And then you're going to be like, hi, chlorine and bromine. There are 3,344 of you. Okay, 2 of you are ClO. All right, so we can say, hi, chlorine and bromine. There are 3,344 of you. 2 of you are ClO. Are you? No. You're something else. And then there you go. Now you just have to add the hydrogens to make it balance. You know chlorine is -1, so you throw a hydrogen in there. Bromine is -1, so you throw a hydrogen in there. And then hydrogen. And then both these guys are -1, so they need 1 hydrogen. But then sulfates, an odd duck, he needs 2 hydrogens. So there's your strong acids. So hi, chlorine and bromine. There's 3,344 of you. 2 of you are ClO. Are you? No. You're something else. I don't know, it's pretty stupid. But anyway, now, so strong acids completely ionize, so weak acids only partially ionize in water. Okay, so that means only some of the acid will actually make the hydronium. All right, so HF is a weak acid, so when it goes, we use this new fancy arrow. So this is your first time seeing this guy. This is an equilibrium arrow. What this is showing is that your reaction can actually go in both directions. So far, we've kind of lied to you a little bit in chemistry. We said, well, we have reactants and they go to products. Now, the truth is most reactions can go by both directions. It just depends on what conditions they're in, all right? And so this is our first venture into this brave new world of reactions that can go backwards, all right? So this HF and this water here, they can react together to form our hydronium and then fluoride ion. But these two guys can combine again, and the hydrogen can go back to the fluorine to form this guy over here. And so that's what this double arrow means, and it's always written like this. So this is known as an equilibrium arrow. All right, these are weak electrolytes because they only break up into ions partially, and so they only conduct electricity partially, especially compared to the strong acids. All right, and then strong bases are strong because they also completely ionize. All right, they break up into their constituent ions. All right, so sodium and hydroxide. Notice that there's no equilibrium arrow here because equilibrium arrow here because it's just completely going to break apart. All right, and these are strong electrolytes. All right, strong bases are group 1 and 2 metals. So those are your alkali metals. All right, and then group 2 was your alkaline earth. What is that? Alkaline earth metals. I think I've been making too many videos today. All right, and so, but notice here that, magnesium is missing from the list. So magnesium is actually not a strong base, but the rest of these guys are. All right, down that list. Weak bases, I mean, it should be pretty obvious that if weak acids only partially dissociate, weak bases would only partially ionize. Okay, and so only some of the base makes hydroxide. So you got ammonia and water, and look, equilibrium arrows. Only part of it will make this guy ionize into hydroxide and sodium, and these guys are weak electrolytes. All right. Now this part is the most confusing of this part, I think, is this idea of concentration versus strength. So remember, we spent a whole lot of time in the previous unit talking all about concentration, what it means, how to calculate it, so on and so forth. And so concentration of an acid or base simply tells us how much of it is dissolved in solution. All right. So what this tells you can have like a 12 molar solution. That means there's a lot of it dissolved in there. You could have like a 0.0000012 molar solution, and it means not very much of it dissolved. So the concentration just tells us how much, of that thing is dissolved in solution. The strength of the acid or base tells us how much of it ionizes or dissociates. So this is an important distinction. So what it really boils down to is that you can have a very concentrated weak acid, all right, a concentrated weak acid. So if I have a lot of HF, hydrofluoric acid, that's dissolved in water, this would be a concentrated HF because there's a lot of it dissolved in water. But HF is a weak acid because it only partially dissolves or dissociates. It only partially dissociates. So that means this specific solution of hydrofluoric acid would be very concentrated but weak. And then down here you have an acid can be strong in nature but very dilute. Dilute's the opposite of concentrated, right? And so if you have only a little bit of HCl dissolved in your water, that HCl would be dilute because there's not very much of it dissolved, but all of that HCl would be dissociated, so therefore it would be a strong acid. So this guy up here, we would classify this situation as a concentrated weak acid, and this one would be a dilute strong acid. This can be kind of confusing, and I've included several practice problems in your packet to help you with this kind of thing. So make sure you do those practice problems, being able to identify, well, what does it mean if it's strong or weak? Because I've only given examples of acids in the PowerPoint, but you also need to be able to do it with bases as well. So it's important to be able to identify if you have a strong or weak acid or base, and then whether or not it's dilute or concentrated. And I won't ask you one that's like kind of in the middle, kind of fuzzy. Like you'll know, like anything over like freaking like 5 molar would be concentrated. Anything less than 1 would be dilute, and then kind of it would be fuzzy in the middle. But anyway, so do your practice problems. This is where it starts to get a little hairy. So make sure you're doing practice problems, thinking about what's going on here. Let me know if you have any questions, and I'll see you on the flip side.